if we compare it with the equation of a straight line, remember that the equation of a straight line is y is equals to mx plus c, where x becomes the variable, x and y are the variables, m represent the gradient of the slope, and c represent the intercept on the x-axis. Okay, now comparing it, we have m2 minus m1, which is a moment variation, becomes y. So our pre-stressing force becomes our x, which is a variable, and we have the intercept as the constant. So if we do that and we have the coefficient, which is this z1 minus z2 over a. So if that is the case, in drawing the graph, we're going to have the graph represented like this. Let's do that. The graph, we're going to have the graph as this. Here represent our moment variation, which is m2 minus m1. We can call it moment variation mv. Okay, so let's call it moment variation mv. All right, so instead of m2 minus m1, let's just call it mv. All right, so we have our moment variation mv. On this axis, the x-axis, we have our pre-stressing force p. Now if we plot the first one, which is equation number 5, we'll have that equation number 5 is a straight line graph. Okay, we're going to have that graph to be a straight line graph. Okay, so having gotten equation number 5 as a straight line graph, equation number 5 as a straight line graph, we'll have equation number 5 represents will be the first, since it appears to have it's most likely to have the higher value due to the presence of z1. Okay, so let's assume equation number 5 to be this. So we'll have this equation 5. Below it uh, we'll have equation number 6. Okay, so let's call this equation number 6. This graph of equation number 6. Okay, so we'll have a graph of equation 5 and 6. The next graph is equation number 7. We have p, which is a variable, and this is going to have a gradient of z1 plus z2 over a. So this graph is going to be a slopy graph because we have a gradient slope. So we draw it this way. So this graph represents equation number 7. Okay, so this represents equation number 7. Now this equation number 7, it represents uh, the minimum value of p. Now if you plot equation number 8, you have it as this. Equation number 8 is coming this way. Let's have it this way. We have our p here. So this is equation number 8. All right, so this is the graph we're going to obtain. We have the graph as this. So let's write here m2 minus m1, a moment variation, which is equal to our mv. Now, having gotten this graph, of course, we know where the graph intersects becomes the solution of the equation. So at this point, we're going to have the point of intersection, which is the maximum. It intersects here at point 6. Of course, you know that at point 6, we do not have, at point 6, we're going to pick the solution from this point. So have the solution, let's call this a value of p. We don't know it, let's call it x. We'll pick another solution here. This is the value of p again. We don't have So we have two values of P. We don't know what to call it. Let's call it Y. So we have two values of P that will give us the solution. So P can either be X or equal. P can either equal to be X or equal to be Y. Now remember, this is an inequality. So of course, we have this part of the equation. So this, you shade this part of the inequality will be shaded. This part of the graph will be shaded. It's not needed. Now for the other side, the side that is not needed is on this side, so we shade this other side. Now for the first graph, we are shading this side. Similarly, we are shading the side of the graph. Okay, so the side we are interested in, if you look at this side, we are really interested in this direction, values from this direction. Also for this curve, we're only interested in value from this direction. You can see that this one is this one is greater than this curve. This curve is greater than this curve, and we have it as that. So this is what we call the graph for the moment variation versus the press-stressing force. So there's a graph of moment variation versus a press-stressing force. So I haven't gotten this graph. The solution of P become X and Y. So we have two values of P and X and Y. Now that is so what it means, that press-stressing force should be either X or Y, or the press-stressing force should be within this boundary. Either it falls from this point of the graph, the intercept at the point of intercept at P to Z. So you can pick a press-stressing force within this boundary. So if here is our zero mark, once you have the value of X, you can pick a press-stressing force within this zone. Zone. Similarly, also, you have the whole of this zone to pick press-stress. You can pick your press-stressing force also within this zone. Okay, you can pick your press-stressing force. And apart from this zone, we also have this zone that is free. You can also pick your press-stressing force within this zone. Okay, so that is what it means with what we have gotten. So you can pick a press-stress. Can pick a press-stress force around the zone. So the most important thing in your design, the first thing you are expected to do, you are expected to have to calculate the value of X. Now, having gotten this graph, we need to find out what X and Y represent. All right. We need to derive an equation for X and Y. So if we have that equation for X and Y, we will be able to solve for P. All right. That X and Y represent what we call the economic solution to the press-stressing force. Now, looking at equation 7 and equation 8, it is obvious from the graph that equation 7 and equation 8 represent the lower and the upper limit of the press-stressing forces. You can see equation 7, you can see the intercept at the counter axis, which represent P. You can see the intercept. So it's obvious that the upper and lower limit of press-stressing force is between 7 and 8. So we can say that the lower limit of press-stressing force represent equation 7. Okay, while the upper limit of press-stressing force represent equation 8. So I would like us to get those equations and get the upper and lower limit of press-stressing force for each of them. Let's consider that now. So we'll say from equation 7, let's start with equation 7. We'll say from equation 7, we know that equation 7, we have it as, let's write out equation 7 again. We have equation 7 as M2 minus M1 less than, we have it less than or equal to Z1 plus F minimum N1 bracket Z2. Okay, this will have, record this will have for, this will have for equation 7. Okay, so we can record this will have for equation 7. We can see it on the board here. So if we have that as our equation 7, so what we are saying is that whatever pre-stressing force P that will be derived from equation 7 represents the lower limit, will represent the lower limit of pre-stressing force. So let's do that, and let's see what we're going to have. Let's look for our P. So if we look for Z1 plus F minimum minus N1 close bracket Z2. Okay, so this will have equal all this stuff is less than Z1 plus Z2 over A bracket P. Okay, so this is what we're going to get. So for us to get our P, what do? It's simple mathematics. Now let's assume our axial forces to be 0. So if we have our axial forces to be 0, we should have this thing to become M2 minus M1, all right, plus, let's work this 0. We're going to have F minimum, all right, we're going to have F minimum bracket Z1 plus, if here is 0 also, we're going to have F minimum Z2. Okay, so this will have closed brackets. Okay, so this is what we're going to have on this other side, and we have all this to be lesser than Z1 plus Z2 over A bracket P. So let's do it in a more simpler form, so that we'll have our P. Let's M2 minus M1 represent our moment duration. So let's call this MV. If we work this out properly, we should have this to be bringing out this as a factor MV plus, we're going to have F minimum bracket Z1 plus Z2. Okay, we'll have it out. Then we have this to be lesser than Z1 plus Z2 over A bracket P. So that P becomes, if this is lesser, so we can say that P bracket Z1 plus Z2 over A is greater than our moment variation M plus F minimum bracket Z1 plus Z2. Okay, so this will have, so the lower limit, which is our P of pre-stressing force, becomes greater or equal to moment variation plus F minimum bracket Z1 plus Z2 all over Z1 plus Z2 over A. Okay, So this gives us what we call our lower limit of pre-stressing force. So we just got in the lower limit of pre-stressing force. So if we like, we can call this equation, the last equation we got, we call it equation 8. You can call this equation 9, if you don't mind. So let's say equation number 9. So we have P is greater or equal to MV plus F minimum Z1 plus Z2 over Z1 plus Z2 all over A. So this is the lower limit of pre-stressing force. Now let's obtain the upper limit of pre-stressing force in this same graph. And of course, we know the upper limit of pre-stressing force represent equation number 8. So with that, you know that you can select a pre-stressing force within that should be greater. Your pre-stressing force you are selecting should be greater than this numerically. So let's obtain that of equation number 8, which is our upper limit of pre-stressing force. Okay, let's do that. Equation 8. This is our equation 8. So let's look for the P, which represent the upper limit. Z2 over A. So if we do that, we're going to have our P to Z1 plus Z2 all over A. Okay, so if we continue on that, we're going to have our P. P will be greater, since this is less, we're going to have P. All right, so this is minus, so we'll have P. Okay, so it means that this is minus P. Solve it, we're going to have minus P brackets Z1 plus Z2 over A P minus F maximum Z1 plus Z2. Okay, so the inequality sign changes because of the negative sign, so we'll divide our through by negative, so we're going to have this as P is less than MV. This becomes negative here, this becomes positive here. F maximum bracket Z1 plus Z2. Okay, and all over Z1 plus Z2 over A. Okay, this is all we're going to have. So finally, we can say that P is less than F maximum Z1 Z2 minus our moment variation over Z1 plus Z2 all over A. So this gives us, let's call that equation 10. So this represents what we call the upper limit of pre-stressing force, like we have seen. Okay, so this represents the upper limit of pre-stressing force. All right, so having done this, we can now tell where, within what boundary range we can pick up pre-stressing force. So once you can solve for equation 10 and you can solve for equation 9, between equation 9 and 10, you can pick it. You can choose a pre-stressing force between equation 10 and equation 9. Okay, so having done that, we've been able to determine the necessary pre-stressing force now. All right, so this brings us to the end of the lecture for today. So in the next series, we are going to write out the necessary equation for the cable zone. Stay tuned. I'll see you in the next series. Before we continue in the determination of the other equations, I want us to look at equation 7 and equation 5, the point of intersection. the various cable zone for each of these pre-stressing force. We are going to obtain it. There are various cable zone for each of these pre-stressing force. We are going to obtain it. Looking at this zone, here we are going to have equation 1A and 4A. So whatever pre-stressing force you are picking from this zone between Y to this point, the necessary cable eccentricity should be gotten using equation 1A and 4A. All right. Similarly, also when the pre-stressing force is gotten between X and Y, the necessary cable zone equation should be equation 1A and 3A. So we have here equation 1A and equation 3A. All right, so wherever a pre-stressing force lies between here, this cable equation for the cable zone should be taken. All right, so similarly, we have here to be equation 2A and equation 3A. All right, so whenever your pre-stressing force is chosen between X and this point, equation 2A and 3A should be chosen for the cable zone determination. All right, so that gives us the necessary equation for the cable zone. So having gotten this cable zone equation, which is the determinant of the choice of pre-stressing force, the next thing we are going to do, we are going to look at the sectional properties. Now we'll look at the sectional properties. You can see the moment variation, Z1 and Z2, which is sectional modulus with respect to fiber 1, which is the bottom fiber, and sectional modulus with respect to fiber 2, which is the top fiber. All right, so we are going to obtain the sectional modulus. Of course, we know that the sectional modulus is the property of the beam that determines the size of the section used. So with this, we know solving for Z1 and Z2, we can size any beam of our choice. So let's go and see, let's solve for equation 5 and 6. We're not going to use equation 7. Of course, we know that equation 7 represents the solving for X in equation 7 does not represent an economic value for the section to be determined. So we're going to be working with equation 5 and equation 6. So let's work with equation 5. Let's determine the sectional modulus with respect to the moment variation. Okay, we can call sectional modulus. All right. So we'll start with Z1. So from equation 5, we can have our Z1 to be since M2 minus M1 is less than Z1 bracket F maximum minus F minimum. Remember, we are not working it in terms of axial stress, but if we're working it in terms of axial stress, our N1 and N2 will be brought into the picture. So, but let's work it just in terms of moment alone. So this will give us, this means that Z1 bracket F maximum minus F minimum is greater than M2 minus M1. All right. So what we are saying is that our sectional modulus with respect to fiber 1 will be M2 minus M1 over F maximum minus F minimum. All right. So we can just represent our moment variation with MV, so that all right. So this is what we have for our section. Okay. All right. So these are sections, so we can say that our Z1 is greater than that. Similarly, also from equation 6, we have equation 6 from equation 6, we have that M2, M1 also lesser than Z2 bracket. We have the same thing, F maximum minus F minimum, okay? So we can also have our Z2 to be greater than M2 minus M1 over F maximum minus F minimum, okay? So this gives us our sectional modulus for this section. Of course, in a situation where we have Z1 and Z2 to be equal, in the case of a rectangular section, where we know that the neutral axis is the same, we can solve that and equate it. Both of them becomes of equal values, okay? So the next thing we are going to do is to obtain the, let's say we can obtain X and Y, like we said. Of course, you can see from the board, X and Y represent our X and Y represents our economic value of pre-stressing forces, and we're going to determine them. Of course, the solution X and Y will be gotten by equating equation 7 and equation 5 together. So the solution to X will be gotten by equating equation 7 and equation 5 together. So that will give us our value for X. So I think we need to establish an equation for X so that we can be able X and Y. So let's start with X. All right. So this equation can be further simplified. We can say that X is equal to F minimum Z1 plus F minimum Z2 plus F maximum Z1 minus F minimum Z1 all over Z1 plus Z2 all over A. So we can simplify this equation further. If we simplify it further, we'll have this cancel this. So we're left with F minimum Z2 F minimum plus Z1 F maximum. All right. So we can say all over what? Z1 plus Z2 over A. So this gives us, we can call this equation, the last equation we got, we can call this equation 11. All right. Let's call it equation 11. So this represents the critical value for our X we got from our graph. So the next thing we'll do is to look to get the value for Y so that we can establish the boundaries. All right. So now let's obtain the value for Y. Now, of course, the value for Y, like we said earlier on, we are dealing with equation. The intersection of Y is at the point between equation 8 and equation 6. We already know that from equation 6, we have M2 minus M1 is less than Z2 bracket F maximum minus F minimum. Okay, that is what we have for equation 6. And from equation 8, we have equation 8 as this. All right, so we have equation 8. We've derived it before, so equation 8, we have equation 8 to be equation 8 to be m2 minus m1 less than, we have less than f maximum bracket z1 plus z2 minus p bracket z1 plus z2 over a. So this is what we have for equation 8. So substituting both of them, if equation 6 is equal to equation 8 at the point of intersection of the two straight line graph, we'll have this to be z2 bracket f maximum minus f minimum, and it's equal to f maximum bracket z1 plus z2, all right, minus p bracket z1 plus z2 over a. Okay, so remember that our p will represent our critical pre-stressing force, which is our y. So we can say that our y, which is equal to our p also, is equal to z2 bracket f maximum minimum fiber stresses all over, we have r here. Okay, so we have this to be minus, we have this to be minus here, y here becomes plus, so we have f maximum z1 plus z2 all over z1 plus z2 over a. Okay, so this gives us our y. So if we solve further, we'll have our y to be equal to f maximum, we have z1 plus z2, all right, minus z2 bracket f maximum minus f minimum, okay, over z1 plus z2 over a. So this gives us the value for our y. So now we've gotten our y, which represent our critical forces. We have two critical forces, x and y. So now we've been able to establish the equation for x and y. Let's simplify this equation further. We can have y to be f maximum z1 plus f maximum z2 minus f maximum z2 plus f minimum z2. Okay, so we can simplify further, and let's see if we can do that to simplify further. So we can have that our y, we have f maximum z1, f maximum z2. So this and this can go. So we'll have f maximum z1 plus f minimum z2 over z1 plus z2 over a. All right, so we'll have that on the board. So if we have this, we can just simplify it. Instead of leaving it in this format, we'll call this one our equation 12. All right, so we round up at this point, getting equation 12 and equation 11 as our critical forces. So the next we are going to do, what we have done today, we've been able to obtain the upper and lower limit of pre-stressing forces. So we know the boundary of pre-stressing forces we are going to choose. We have also been able to determine the critical forces X and Y. And we've also established the various cable zones for every pre-stress force choosing. Okay, so also take note that when you have a situation where your Z1 is equal to your Z2, in the case of most rectangular beams, you are going to have X to be equal to Y. All right. So if your critical force X is equal to your critical force, when you have your critical force S to be equal to your critical force Y, we can determine either of them, X or Y, by saying that pre-stressing force X or Y or P, we can say that X or Y is equal to A over 2, because when here becomes the same, here we have this plus this gives you 2, and this gives you this gives you this. So we'll have it as A bracket F maximum plus F minimum. All right. So this gives us our X or our Y, where we have the sectional modulus with respect to fiber 1 and fiber 2 to be the same. All right. So those bring us to an end to this lecture. In our next class, we will be dealing with the cover requirement of a non-composite section. Thank you very much for watching. Please do well to hit the subscribe button or make a comment if you do enjoy the lectures. I'll see you in our next class. Stay cool.